Students, we will continue with oscillations. In the last class, we discussed what is a periodic motion, oscillations, and what is the equation of simple harmonic motion, what is simple harmonic motion, all these things we have already discussed. So, we calculated the kinetic energy and potential energy in case of simple harmonic motion, the velocity, acceleration, kinetic energy, total potential energy and total energy, and we found that the total energy remains constant. Now, in this we will continue with that. This is what we did. This is the equation of simple harmonic motion. I can write k by m is equal to omega square x. This is acceleration. This, if x is displacement, d square x by dt square will be your acceleration. Acceleration plus omega square, I have placed k by m is equal to omega square. So, omega square x equals to 0. That means, omega square can be written as, if you take this out, this to the right hand side and divide it by x, x is your displacement, this is your acceleration. So, omega square, neglect that negative side. So, it will be acceleration by displacement, omega square. So, omega will be square root of that. The solution of this equation, we found that this will be x equals to a sin omega t plus phi, where phi is the initial phase, and when t is, if we measure that when t is equal to 0, suppose x is 0, then x will be 0, this is not 0. So, this is 0, that means phi must be 0. So, if you measure the time from the point of the mean position where x is 0, because distance or displacement is measured from the mean position. So, whatever is the displacement from the mean position, that is x. So, here if x is 0, then I measure the time. The mean time ro 0 arambha hoba from the mean position, when the body is at the mean position. So, phi is 0. So, I can neglect this phi and I can write this is my solution. If this is the solution, you see that this is periodic, that means it has a period, time period capital T, we have already defined that. So, a sin omega t time re jaha t plus capital T time re madhya seya. So, this is equal to omega t plus, but we know that sin omega t repeats after 2 pi interval. Tamane sin omega t is equal to, this is equal to a sin omega t plus 2 pi. Tamane ethi hela eta omega t into capital T. So, tamane omega into capital T is 2 pi, that is what I have written, or capital T time period is 2 pi by omega. Tamane time period can be written as 2 pi 1 by omega. So, by omega 1 by omega hobo yar ultata, the displacement by acceleration the square root. If we take the example of the simple pendulum and the mass spring system, in the case of simple pendulum, this is the mean position, this is the mean position. From here you displace it to one side and leave it here. When you leave it, this comes to this point, where by the time it comes here, its velocity is quite large, it cannot come to rest. So, it goes to overshoots this side. From here it comes back, because here the velocity is 0. So, when the velocity becomes 0, it comes back, but by the time it comes here, its velocity is quite large, it cannot remain at rest. So, it overshoots to this side and again it comes to this point. So, it completes one oscillation, this again the whole thing is repeated. Now, why this force? What is the restoring force which is trying to bring it back to the mean position? If mg, if I draw the free body diagram of the simple pendulum mass, here if m is the mass, mg is the weight acting downward vertically. Now, I can find out a component along this thread, mg cos theta and another mg sin theta. Mg cos theta tension T will be equal to mg cos theta. So, they balance each other out. What remains is minus unbalanced force, here is minus mg sin. Why minus? Because x is measured from here to here, this displacement, but it is towards this direction, that is why this negative sign. So, force is equal to minus mg sin theta, means force is in the direction opposite, or it is always towards the mean position. When it will come to this side, force will be along this direction. So, it is trying to bring it back to the mean position. So, force is simple harmonic motion by duita haba darkar. it should be periodic, it should be oscillatory. Third thing is that acceleration should be proportional to displacement and it should be directed towards the mean position. So, ये चारटा का जिनस होचे हमर एटी. It is periodic, repeat करूची. It is oscillatory, to and fro about the mean position. Second वाला. Third is force is directed towards the mean position and whether it is proportional to it or not. What we see that here m into acceleration is minus mg sin theta. So, acceleration is minus g sin theta. If your angle theta is small, you can write minus g theta. Tamane sin theta is nearly equal to theta if your theta is small. So, minus g theta. So, theta can be written as, here theta can be written nearly equal to tan theta. So, if you write it as tan theta, in this triangle you see the tan will be perpendicular over base. So, perpendicular over base is this length. So, this length is L. So, x by L. So, I have written tan theta, theta as tan theta is x by L. So, minus g x by L. That means, g is constant, acceleration due to gravity, L is the length of that string to which the simple pendulum is attached. I have shown it here. So, g by L are constant. That means, force is acceleration is proportional to minus x. So, this is SHM, it is proportional to the displacement, it is towards the mean position. So, all the four requirement, periodic, oscillatory, proportional to the displacement and directed towards the mean position. All these four things have been satisfied by this motion. So, this simple pendulum motion is simple harmonic. And hence, we can find out the C use omega square jagare g by L lekhaichi, tamane omega hela amaro g by L root over. So, if it is and time period is 2 pi by omega, you put it and you get this is the time period of the simple pendulum. Similarly, you can find out the case of a mass spring. In the case of mass spring, here I have taken horizontal, one can take also vertical motion. So, when you stretch the spring, bring the mass to this point, this position and leave it. So, when you leave it, whenever a spring is stretched, there according to Hooke's law, there will be a restoring force. It will try to regain its original shape and size, and hence that restoring force is proportional to the extension. So, here extension is x. So, F is proportional to k x, proportionality constant is called spring constant. This is k is our spring constant here. And F is proportional to x. So, I write F is equal to minus kx. Minus, why? Because my x is from this point to this point, but force is opposite. This is the direction of force. The force is a restoring force. So, it is opposite. So, this will come to this point. By the time it comes here, again its velocity is quite large. Again it will compress the spring and come to this side. From here it will go back again to the mean position, then to this position and this way. So, this will undergo a to and fro motion about the mean position. When the spring was at rest, unstretched spring position jaha thila, seita hochi tara mean position. Now, beyond that, जोटी कि तमे नहीं गला सेटा पॉजिटिव मैक्सिमम सेटा एम्पलीट्यूड पोजीशन, मैक्सिमम डिस्प्लेसमेंट पोजीशन, एक्सट्रीम पोजीशन, फ्रॉम देयर इट विल कम टू दिस कंप्रेस हला परे से फेरेबो, कंप्रेशन कर दबो जदि स्प्रिंग कहबो नाही मु ओरिजिनल को जीवा को चाहूची. सो इट विल ट्राई टू रिगेन, ता माने से एठू से याड को आनी तड़ीबो ताकू. So, that is why it will come to this point, from here it will go to this. So, in this manner the to and fro motion of the spring will take place, which is simple harmonic, and it is the direct सीधा देखो ची force is proportional to x and negative direction, ता माने k बाकी रहला m टाक मु हरण कर देली एठी d square acceleration plus k by m into x is 0, ता माने k by m लिखाई ची. If you compare with the original equation, then this is d square x by dt square plus omega square, k by m jagare omega square लिखाई ची. ता माने omega square is k by m. So, time period is 2 pi by omega. So, t is 2 pi by omega, 1 by omega रो value माने यार उल्टा टा, तो m by k रो root over. So, this is the time period of mass spring method. So, this is how we can show that both the spring as well as the simple pendulum undergo simple harmonic motion, and in both the cases force is proportional to displacement towards the mean position, or you say acceleration, because force re khali mass ta harana kardela you get the acceleration. So, mass constant tenu force jodi proportional hela tabe acceleration madhya proportional. So, acceleration is proportional to displacement, or you say force is proportional to displacement and opposite to displacement, or in other words always towards the mean position. So, both the cases we found out the time period. Now, you can find out in the last class we found out the kinetic energy. You should know the formula kinetic energy half mv square. This is the x, taku differentiate kale you will get the velocity, tar square nahi gale you will get the kinetic energy. Potential energy is half kx square, k is m omega square. So, half m omega square x square. So, you should draw the graph and see the graphs of these. If you draw the graphs, you will see that this is some constant into x square, ta mane gote parabola. So, this is my potential energy graph with x energy. Jodi mu draw karibi, it will be like this. Whereas kinetic energy, you will see that this will be half m a square minus x square. So, this graph will be opposite to this, and for all points of x you find that this plus this jodi karibo, it comes out to be a constant. This value is half m omega square a square. This we did in the last class. You should draw the graphs of this kinetic energy and potential energy and the misana pholo. Eta kinetic energy, total energy graph. Total energy remains constant wherever the particle is. X jaha hi thau, total energy will be constant. So, this much all these things about simple harmonic motion and spring constant. The time is short, I could not go into the details of the spring constant things, and we will move over to the further things, that there are these motions that we have discussed are free motions. What is free motion? Free oscillation. So, free oscillation, then damped oscillation. So, free oscillation means when a body oscillates with its natural frequency. It is not oscillating due to someone else. It is not oscillating by a driven force. There is no driven force. There is no other oscillating body which is trying to oscillate it. So, in that case we say that it is a free motion or a free oscillation. Like your simple pendulum, thore taku disturb kardela chhadi dela. Se tara ape whatever is the force there coming in the system, that force is making it move. So, this is a free motion of the simple pendulum. Similarly, in the case of mass and spring also, once you disturb and leave it, it continues its motion, to and fro motion. Mass will move like this, and we say that it is a free motion. It will oscillate with its own natural frequency. Frequency, see the time period we found out is 2 pi root over of L by G in the case of simple pendulum. So, frequency is 1 by T. So, yara ulta ta inverse kar dabo, you will get frequency. So, the G is constant, 2 pi constant, L hela length of the simple pendulum. Tamane length of the simple pendulum determines the time period. तार लेंथ जति थिबो से हिसाब रे तार टाइम पीरियड हबो. जो जिनस भी नियो तमे लेंथ जदि समान रहिला सिंपल पेंडुलम रो तळे तमे जहा लगाओ जो गोटे सॉलिड बॉल लगाओ और यू पुट ए होलो बॉल डजंट मैटर. In all the cases the time period will be same if the length of the simple pendulum is same. So, that is its natural frequency. Length determines the natural frequency of the simple pendulum. Similarly, the type of spring, spring constant means it depends on the material of the spring, केते टाण अच्छी ना ढिला अच्छी, जल्दी टाणी ही जाउची ना जल्दी टाणी होउनी, बहुत stiff अच्छी spring टा, that determines K, the spring constant. So it depends on the spring constant. In case of mass spring system, the spring constant determines the time period. So if that is remaining same, then the frequency will remain same, because time period same, t ro inverse कर देले frequency, so it has a natural frequency. So that is called a free oscillation. But forced oscillation, or before that let me say what is a damped oscillation. When a body oscillates, in presence of dissipating forces, तमाने एठी कौन होबा, the amplitude of the body gradually decreases, amplitude gradually decreases, and we call it, this decrease of amplitude is called damping. So in case of a simple pendulum, when I am saying that the motion is repeated, that means it goes same distance to both the sides. But if there is friction in air, then it will reduce the energy of the total energy of that simple pendulum will not remain same. So what will happen, gradually एतिकी बाटे जाइथिबो, एतिकी गला, फेरिला बेलू एतिकी जावा गला, किंतु नेक्स्ट टाइम गला बेलू एठी तार कमी जीवो, से एमती ता माने एठी की पुणी एठी फेरिला, एठू फेरिकी एठी की आसीबो, एठू पुणी कमी गला, पुणी एठी भी कमी गला. So gradually तार this motion will be like this. This you have observed in daily life, that if you leave a simple pendulum, ताकू धीरे 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 से आसिकी रेस्ट हो जीवो. Why it has come to rest? Because its energy has decreased. कुआडे गला ता energy? Because friction in air. Due to the friction in air, it loses some energy, and that is why it cannot keep the same amplitude. It cannot have the same displacement on both sides. So gradually the oscillation gradually decreases, the amplitude decreases, and gradually it comes to rest. So this is called a damped oscillatory motion, that there is damping, there is decrease in amplitude because of the damping forces. That means we can draw that the oscillation are like this, instead of remaining constant, gradually the amplitude is decreasing and decreasing and decreasing and becomes 0. ये केते जदि मु एटा बहुत बड़ नहीं गली, suppose this, where it should have been constant. In ideal case, it should have been constant like this, but instead of remaining constant, gradually this amplitude is decreasing, and this is like an exponential graph. This is e to the power minus some bt by 2n. So this is something like an exponentially decreasing graph. So the amplitude exponentially decreases, and because there is dissipating माने loss होची energy, there is loss of energy. So dissipating forces means forces which cause the loss of energy, like friction in air, viscosity in the medium, all these things are dissipating forces or decreasing loss of energy jaha jogu हुए, we call them dissipating forces. So that is called damped oscillation. Now forced oscillation, there is another, when a body oscillates, in presence of a driving oscillating force. Or agency. Now, in this case, it is driven by some other oscillating body. For example, you take, I do not have any way to show this whole thing, but suppose you take a rigid support and a rigid support here and tie a string, some or put a bar or something solid and rigid thing, and from a rigid support you hang two, let us say minimum 3 simple pendulums. Now, you 1, 2 and 3. Now, if I oscillate 2, only disturb 2 will oscillate with its own time period. It has own frequency, it will oscillate with its own time period. Now, see what about 3? 3 also will oscillate its own time period if you measure that. Now, suppose while these two are oscillating, let us say 2 and 3 dita ko tame halai delo, both will oscillate. Then after a few seconds you start 1. I have see 1 and 3 have the same length, so they will have the same frequency, actually natural frequency tankara same. Now, if I oscillate now 1, कौन हबो ना किछ समय पर तुम देखिबो जे 2 3 जो oscillate करूथिले 2 because 3 रो oscillation frequency जहा 1 रो oscillation frequency से या it will continue to move with the same frequency initially frequency. 2 रो जो frequency तो अलगा थिबो कारण तार length ता अलगा अछि, but 2 will initially it was oscillating with its own frequency जति समय नौथुला से थरे जीवा पई सेटा जहा थिला धीरे धीरे सेटा कमी जीवो and it will die out and it will start oscillating with the frequency of 1. ता माने लेट्स से 3 टा को मु छाडी दोची धरा जे 1 आउ 2 को नै के खाली करिवि ता माने 2 ता निज फ्रीक्वेंसी ता 0 हे गला आगो तार oscillation 0 हे गला, then it starts moving with the frequency of the driven force. किए ड्राइविंग करुची 1 ताकू ड्राइव करुची बिकॉज 1 रो oscillation तार जो फोर्स टा या कम्युनिकेट होची. So in this case 2 is oscillating under the action of the force due to 1. So in this case the oscillation of 2 is called forced oscillation. ताकू तुमे बाध्य करूच जे तू मो oscillation मु जेमती भाबरे जाउची मोर फ्रीक्वेंसी जहा तोर भी फ्रीक्वेंसी सेया हो. So this is what the forced oscillation says, that when a body oscillates in presence of a driving agency, driving force, and that force is oscillating also. So in this case what happens, initially the body, the original body oscillates with its natural frequency, the nija frequency, it is his own frequency. Gradually this oscillation will decrease, the oscillation will decrease. If you oscillate karuthula, you apply the driving force or driving oscillation, ता माने एक को तुम डिस्टर्ब करो oscillate कला बर्तमान एक तापरे कौन होबो ना एई तार जो ओरिजिनल ऑसिलेशन थिला these oscillations gradually will decrease तार ओरिजिनली जहा थिला decrease हेकरी धीरे धीरे then it oscillates decrease to 0 and then it oscillates with frequency of driving force or impressed force. Whatever is impressed on it, what is it driving, that तार frequency जहा ता माने बाहरु जी apply करूची एक ताकू करिवो. Then comes resonance. When the frequency or omega or frequency of the body natural, this is the natural frequency, if this is equal to the frequency of the impressed force or driving force, F stands for frequencies, remember. If the frequencies of the natural frequency of the body is equal to the frequency of the impressed force, then amplitude is infinite. Amplitude of force, amplitude becomes very large. This phenomena is called resonance. That when the natural frequency of a body is equal to the frequency of the impressed force, whatever is the force impressed on it, जे ताको ड्राइव करबा पई एक्स्ट्रा फोर्स हमें देले, दैट तार फ्रिक्वेंसी और यार फ्रिक्वेंसी जदि दीटा कर फ्रिक्वेंसी समान थिबो, यार नेचुरल फ्रिक्वेंसी और यार फ्रिक्वेंसी इम्प्रेस्ड फोर्स रो फ्रिक्वेंसी दीटा को जदि समान हे गला, यू विल सी दैट दिस विल oscillate with a large amplitude. So, that large amplitude shows that there is a resonance. That means, मु वर्तमान 1 2 3 2 3 को oscillate कर देबी, तापरे 1 को oscillate करीबी, कौन हबो ना 2 तो 2 रो प्रथमे तो अलगा तार फ्रिक्वेंसी, से प्रथमे आगे ता फ्रिक्वेंसी कमी कमी तार oscillation कमी कमी जीवो, कमी गला परे तापरे से 1 रो फ्रिक्वेंसी संगे जीवो. 3 कौन हम, बिकॉज 3 रो फ्रिक्वेंसी नेचुरल इज इक्वल टू द ड्राइविंग फोर्स रो फ्रिक्वेंसी. सो 3 रो देखिबा एम्प्लीट्यूड बहुत बेसी हबो, से बहुत जोर जीवो. सो फ्रॉम दैट आल्सो यू कैन नो दैट द यार नेचुरल फ्रिक्वेंसी या संगे समान, जोटा इम्प्रेस्ड फोर्स है ता फ्रिक्वेंसी संगे समान. सो दैट इज व्हाई मेनी टाइम्स व्हेन ट्रूप्स आर मूविंग ऑन ब्रिज, ब्रिज ऊपर गला बेले सब ट्रूप जो धर आर्मी गोटे गोटे वन स्क्वाड्रन और वन ट्रूप इज गोइंग ओवर ए ब्रिज, ब्रिज तले गोटे एयर अच्छी. सो व्हेन गोड़र ये जो जोता माड़िक से जाऊँ जोतारे मच मच करी गोटे गोटे पर्टिकुलर ऑसिलेशन रे से माने गोड़ को पकाउछंती. सो इट विल वाइब्रेट द एयर बिलो द ब्रिज, ब्रिज तलर एयरटा वाइब्रेट करिवो विथ अ सर्टेन फ्रिक्वेंसी. तो गोड़ ठीक भाव में पड़ुची, पूरा एकदम मार्चिंग बहुत बढ़िया होची एवं दे आर इन यूनिसन. देन व्हाट हैपेंस, इफ इट सो हैपेंस दैट द नेचुरल फ्रिक्वेंसी जो फ्रिक्वेंसी रे तांका गोड़ पड़ुची से फ्रिक्वेंसी जदि इक्वल हो गला, से जो तले जो एयर अच्छी से एयरटा भाइब्रेट करिवो. एयर रो भाइब्रेशन रो गोटे फ्रिक्वेंसी अच्छी तार निजर, बिकॉज तार लेंथ केते, तार हाइटटा केते, केते अमाउंट रो एयर अच्छी सेठी लेंथ एंड ब्रेड्थ. So, accordingly it has a natural frequency. से natural frequency सांगरे आंका गोड़ पड़ीवार जो natural frequency जदि समान हो गला, then the breeze will also, the air will vibrate with large amplitude and hence the breeze will also vibrate with large amplitude. In that case the breeze will collapse because it will vibrate with a large amplitude. In fact, mathematically speaking or theoretically speaking, the amplitude will be infinite. And that means it is a large amplitude. So, the breeze may collapse. So, that is why whenever troops are moving over a bridge, they are asked to go off beat. That means सेमान तांका गोड़ पूरा ताल मिलेगी चलिए बेतालिया चलिए, so that it is not a frequency दीटा को मैच करिवनी जेमती. That is the reason. There are many other reasons you go through. There are many other examples in which you will see that you will hear तमें पानी गोटे जगरे रखिकी गोटे ट्यूनिंग फोर्क को वाइब्रेट कले, you will see that for a particular length of water in that tube you will hear a large sound, मैक्सिमम साउंड. किंतु लेंथटा जदि समान कम बेसी करदेले साउंड सुना जीवनी. दैट मीन्स ट्यूनिंग फोर्क रो फ्रिक्वेंसी, दैट इज द इम्प्रेस्ड फोर्स, सी वाइब्रेट करुच्ची एयर को, से एयर रो वाइब्रेशन जेति की जहाँ नेचुरल फ्रिक्वेंसी आउ ए ट्यूनिंग फोर्क रो फ्रिक्वेंसी दीटा को मैच करिवो तेबे एयर विल वाइब्रेट विथ ए लार्ज एम्प्लीट्यूड एंड यू कैन हियर ए साउंड देयर. सो दिस इज अबाउट ऑसिलेशंस एंड वी विल मूव ओवर टू वेव्स. I shall not be able to complete because there is a time constraint. And now what happens here, we have read about oscillation of a single particle. One particle is disturbed and left, it oscillates with a certain frequency. It may oscillate like this or it may oscillate like this. Now what happens when there are a number of particles and there is some disturbance जे कि थरक माने किछि टाइम छाड़ी छाड़ी गिरी आग याकू डिस्टर्ब कला तापरे ताकू डिस्टर्ब करिवो तापरे ताकू डिस्टर्ब करिवो तापरे ताकू डिस्टर्ब करिवो what will happen. So if you have a medium in which there are many particles and there is a disturbance disturbing these particles one after the other, not at the same time, one after the other, there is a phase difference. Se kou samay re pahunchila tanka pakku, there is a time gap and that time gap determines the phase difference. So prathame yaku disturb karibo tapare yaku karibo tapare yaku karibo. So after certain time interval, suppose I will say that these particles it disturbs, tamane disturbance ta सीधा जाउची, किंतु ये जो particle of the medium say these or the constituents of the medium, these medium let us say oscillate, tamane ये disturbance टा गोटे oscillation create करूची. So oscillation कहार oscillation, particle मानकर oscillation. एका संगे समस्त को उठाउची पकाउची ना, जन को उठैला आग तापर जाइकरी नेक्स्ट को पकेला, ता माने कोन हबो ये ऊपर को पळे गलानी एते बाट एठी पहुंची गला, सेठी डिस्टर्बेंस पहुंचीला जाइकरी सेकंड पार्टिकल रे पाखरे पहुंचीला. सेकंड पार्टिकल ता माने आई एम सेइंग दैट these particles will let us say oscillate like this but not together. जदि एका संगे उठी कि थाते एठी पहुंच थाते तबे तो धर सबु जाक सीधा रहइबो. But what happens that something like a water, in the water you put a stone, what you see is that circle, there is something travelling outward, you see some circles and something is travelling outward and the water surface कोठी ऊंचा हो जाउची कोठी नीचा हो जाउची. So that means the shape is something like this. Why? Because when the disturbance, what was the disturbance? तुमे stone जो पकेलो सेही टू disturbance टा start हैला and it moves radially outward and on the while it goes like this, it disturbs the particle, the water particles on its way. First particle टा धरा आसी disturb हैला, से first particle टा धरा जाऊ एठी की पहुंची गलानी. Second particle पाखरे जेतेबेले से पहुंचीला, when the disturbance reach the second particle, धरा जो disturbance एठी की आसी पहुंचीलानी. सेही समय भितरे ये एठी अछि, ये किंतु सेतिकी बाट जाई नथिबो कारण पछरे ता पाखु डिस्टर्बेंस टा पछरे आसिला, से पछरे डिस्टर्ब हेची, तेनु से सी जेतेबेले स्टार्ट करी करी एठी पहुंचीची. थर्ड पार्टिकल टा धरा एठी पहुंचीची, फोर्थ पार्टिकल पाखरे जस्ट पहुंचीची डिस्टर्बेंस, तामाने ये एठी अछि. सो ये ऊपर को जाउची, ये भी ऊपर को जाउची, ये एठी अछि. So the shape of this surface will be something like this because the particle gote particle एठी अछि, गोटे एठी अछि, गोटे एठी अछि, गोटे एठी अछि. So by the time the disturbance reaches to this side all, you will see that a particle टा कोन हेतिबो ना ऊपर को जाई तळकू आसी तळकू एठी पहुंची गला फेरी गला. ता पर particle टा पूरा फेरी पारि नथिबो तार ओरिजिनल पोजीशन को, से तळे थिबो को टिके तळे थिबो, ये आउ टिके तळे थिबो, आउ टिके बाट अछि तार जिबा पई, ये आउ टिके तळे थिबो. So in this way you will see that the shape, these are the position of the particles of the medium, किए कोठी अछि, these particles are here and what we see is an envelope of their positions and we say that a wave is travelling. So the envelope of this position of these particles determines the wave. But what is the wave? The wave is the disturbance. It is the pattern of the disturbance which is moving out. तामाने वेव रो वेलोसिटी सीधा जाउची से सी एमती ऊपर तळ एमती होउनी, सी एमती होउनी. वेव इज ट्रैवलिंग इन दिस मैनर. प्रथमे याकू डिस्टर्ब कर दला, धर प्रथम पार्टिकल को डिस्टर्ब कला, सी तार एमती एमती हैला कि ऊपर को एमती एमती हैला. तापर नेक्स्ट पाखु को गला, नेक्स्ट वाला को डिस्टर्ब कला, सी ऊपर को पळेलानी टिके बाट, ये तापर जीवो तेणु पछरे रहिची से. तापरटा को गला सी टी आउ टे पछरे रहिबो ये आगो को पळेइबणी किछि बाट तापर ये आरंभ करिवो सो इन दिस मैनर इफ यू इमेजिन जस्ट आई हैव नो टाइम एक्चुअली टू ड्रॉ ऑल दिस इंडिविजुअल टाइम प्रति टाइम रो इंडिविजुअल रो मु ड्रॉ कले यू विल सी दैट if each of these particles are oscillating they will keep oscillating at their own position जो जगह रे से माने थिले सेठी रहितिबे they are not moving with the wave so there is a disturbance which is moving outward with certain velocity and disturbing the particles of the medium. These particles move oscillate, they either oscillate perpendicular to the wave direction or they oscillate parallel to the wave direction. So in both the cases एमती भी वेव एमती जाउची से माने एमती एमती ऑसिलेट करिवे सेटा भी पॉसिबल सेटा साउंड वेव रे हमर वी हैव दैट काइंड ऑफ ऑसिलेशन सो पार्टिकल्स विल ऑसिलेट व्हेन दे ऑसिलेट एट एनी गिवन टाइम द पोजीशन ऑफ द पार्टिकल्स गिव्स अस द पैटर्न ऑफ द वेव सो द पैटर्न ऑफ डिस्टर्बेंस सो वेव इज दिस इज व्हाट इज अ वेव इज a pattern of disturbance which moves disturbing particles of the disturbing constituents of the medium one by one. One after the other and the constituents here I constituents माने सेटा air layer हेई पारे गोटे particle हेई पारे so that is why I am saying constituents. The constituents oscillate simple harmonically SHM but do not move with the wave. There is no transportation of the particles. The particles remain at their own position. निज जगार थी खाली भाइब्रेट करेंगे भाइब्रेशन पैरेलल हो पारे टू द डायरेक्शन ऑफ वेव or it may be perpendicular. What is wave? Wave is the disturbance. It is the pattern of disturbance that we see. When disturbance travels, disturbing the particles of the medium or constituents of the medium, the constituents of the medium do not move with the wave, but they oscillate at their own position in simple harmonically. Then the pattern of the disturbance is called a wave. So wave is a disturbance. Remember, wave straight जाउची wave oscillate करूनी किछि जिनस who oscillates the particles or the constituents of the medium oscillate they do oscillate may be perpendicular when and that is why we have two kinds of wave transverse we can define types transverse or longitudinal. What is transverse? When particles oscillate perpendicular to the disturbance, perpendicularly to the wave direction. And when particles oscillate parallel to the wave direction, then we say it is a longitudinal wave. Best example of a transverse wave is our light wave is transverse wave. The sound is a longitudinal wave. So, if the particles of the medium oscillate parallel to the wave direction, it is a longitudinal wave, or if it moves perpendicular to the wave direction, then the wave is a transverse wave. So, transverse wave in all the kinds of waves that we will come across, there will be electromagnetic waves, which is light is an example of that, and it is transverse. Then we have mainly mechanical waves. The mechanical waves may be waves in a string, something like when you are vibrating a violin wire or a sitar or a guitar, all these are transverse, all these are mechanical waves in a string, or it may be sound is a mechanical wave or water wave is a mechanical wave, all these are mechanical waves. And we will also come across matter wave. This you will read in your atomic physics chapter. So, we will not go into the electromagnetic wave, we are more concerned about the mechanical waves, mainly the sound waves. So, mechanical waves require two properties of the medium should be there. One is elasticity and inertia. Because of the inertia property, the velocity cannot become 0 instantly. So, that is why the particle will not come to rest when it is moving. Suddenly it will not come to rest. That means, suppose water re gote particle, this particle is disturbed, and it moves up. Ethi gala, ethi maximum ethi ta velocity 0 he gala. Now it comes back, comes to this. When it comes here, by the time it comes here, its velocity is quite large. Its velocity cannot become 0 instantly, and that is why, because of inertia property, it overshoots. It continues in its state of motion. So, its velocity, with its velocity it continues. So, that is why that is the inertia property. And elasticity, because the medium wants to come back, elasticity is the property by virtue of which a body tries to regain its original shape and size. Because the water molecules, they want to come back to their original shape, original straight jaha thila, jemti upar surface re thila, seti rahiba ku chahunchunti, and that is why when you disturb it, it tries to come back. So, but here it cannot remain at rest, so it overshoots. जदि तलक पड़ेगा एठिक आसिक एठी पहुँचला पर ता वेलोसिटी धीरे धीरे कमीगला, एंड वेलोसिटी बिकम्स 0. इट ट्राइज टू कम बैक बिकॉज ऑफ इलास्टिसिटी. सो इट ट्राइज टू कम बैक, एंड बाय द टाइम इट कम्स हियर अगेन इट्स वेलोसिटी इज लार्ज, सो पार्टिकल गोज अप. So, that is why it moves up and down like this. So, water wave for example is a mechanical wave, and in that case we can say it is a transverse kind of wave. In this case the particles are moving up and down. So, then in case of sound wave, suppose here I make, this is the source of sound. When a sound is produced, it vibrates, that is because of the vibration of that source. When that vibrations, suppose it vibrates the air near it. So, this air you can consider to be consisting of many layers. So, it vibrates the layer. Suppose it presses the, so what happens here, that there will be pressure, there will be the air layer will be compressed. जदि ये सब लेयर को से चापी दब एमती धर फोर्स याडे जाउची, सो इट विल ब्रिंग द लेयर्स क्लोज टुगेदर, दैट इज कॉल्ड ए कंप्रेशन. सो लेयर्स विल बिकम क्लोज बाय एमती पाखापाखि हो जिवे. ये जदि पाखे गला तबे ता पूर्वर लेयर गुडाक टिके दूरे दूरे जिवे. सो दिस इज कॉल्ड ए रेयरिफैक्शन, and these where the layers become close by is called a compression. So, when sound is produced by a source, it compresses the air near it, it pushes the air near it. Because it pushes the air near it, so all the layers se taku ta next ko push karibo, se ta pakhaku palebo, se third fourth pakku palebo. In this manner the layers get compressed. तेणु कंप्रेशन आगु आगु एमती आगु ए लेयर सी ताकू करीगला तापर पोर्शन रे विल बी. सो दिस लेयर ता पूर्व लेयरटा जदि ए लेयरटा याड को घुंची गला तामाने एपटे खाली हो गला जगह, तामाने दिस बिकम्स अ रेयरिफैक्शन, डेंसिटी बिकम्स लेस एंड दैट इज कॉल्ड ए रेयरिफैक्शन एरिया. सो रेयरिफैक्शन अच्छी तामाने से फेरिया को चाहूथुबे, सो ये तो सेठी जाइए चापी रही से पुणी भाइब्रेट कर से एवरी लेयर इज भाइब्रेटिंग तेणु सी जो फेरवा को चेष्टा कर सी कौन कर बर्तमान ये जो रेयरिफेक्शन थिला एठू से खोलवा को चेष्टा कर सो ये जो खोल तब आग को सी तापर जिते पुणी फेर इड़ को नेक्स्ट लेयर को कंप्रेस कर सो दिस इज ए कंटिन्यूअस प्रोसेस यू इमेजिन जे प्रथमे चापीदेला समस्त को से चापीदेला ये चापीवाटा एठी आसी पहुँचला बाय दैट टाइम इट रिचेस हियर सेते को से फेरवा को चेष्टा करने ये गुड़ाक सब रेयर होकर अच्छा एमती किसी समय पर ये सब रेयर होकर अच्छा से पहुँची गले एठी पहुँचीगला तार किसी समय पर ये जो एमती फेर ये एमती एमती चापा चेष्टा कर से इे चापा चेष्टा कला बेलू धर से पहुँची एटी आसिक चापा जिनसा ये पहुँची यही पोर्सनटा रेयरिफेक्शन होती ये एटी पहुँचला बेलू याडू पुणी ये पुश करुच्ची तेणु ये आहरी पुणी ये पुणी फेरवा चेष्टा कर ये जो फेरवा चेष्टा कला बेलू ये पुणी आग को पलि सो इन दिस मैनर एट एनी पॉइंट ऑफ टाइम what you see is some layers are close by near to each other, then there is a region where the density is less, layers are far apart, then a portion where the layers are close by, again they are compressed. So there is a compression, there is a rarefaction, there is a compression. So after a certain time interval at any time t, what you see is the air consists of alternate compression and rarefaction. So this is a compression, this is a rarefaction. Rarefaction is the portion of the medium where the layers are far apart or away from each other, the density is less. Compression is the portion where the layers are close by because they have been pressed, it is pushed in this manner. So compression and rarefaction. So longitudinal wave consists of compression and rarefaction. Whereas in the case of transverse wave, कौन हम ये ऊपर को तल को हम here it is parallel longitudinal wave the particles are moving parallel to the wave direction they are moving parallel to wave who the particles of the medium are moving parallel to the wave then it is a longitudinal they are oscillating parallel to the wave not moving only they are oscillating. So in transverse wave the particles will oscillate perpendicular to the direction of wave आगु को आगु जाउची wave किए disturbance so a particle ऊपर को गला ता माने at some point of time what you will see that the a particle टा ऊपर अछि ये तळे अछि एमती position that means here or some particle is here one particle is here or particles are here like this. So in this case we say that this is a crest जोटा maximum ऊपर position टा and this is a trough and we say that a transverse wave consists of a crest माने height रे maximum जोटा point टा सेटा हला हमर crest point a crest and lowest point टा हला हमर trough. So transverse wave consists of crests and troughs whereas longitudinal wave consists of compressions and rarefaction. Here the particles oscillate parallel to the wave direction, here the particles oscillate perpendicular to the wave direction. Wave is moving in all the cases I am showing wave is moving from left to right, some disturbance is moving, the disturbance is making the particles to oscillate. So oscillation अच्छा एका टाइम रे तांको डिस्टर्ब करूनी ता माने जनक परे जनक डिस्टर्ब करूची सो देयर इज ए फेज देयर विल बी ए फेज डिफरेंस समस्ते एका फेज रे रहिबेनी बिकॉज डिस्टर्बेंस तांका पाकु डेरी रे आसिला का पाकु जल्दी आसिला का पाकु डेरी रे आसिला सो दे विल नॉट बी डिस्टर्ब्ड एट द सेम टाइम एंड दैट इज व्हाई वी से दैट देयर इज ए फेज डिफरेंस बिटवीन द each particles all the adjacent particles भितर गोटे फेज डिफरेंस अछि काहे ना वेव ता पाकु डेरी रे पहुंचला. So this is what is a longitudinal wave, a transverse wave, and how the longitudinal wave consists of compression and rarefaction, example sound wave, and how it moves, the equation of wave. for a solution for displacement relation. Now, what we want to find the displacement relation, that in this case now there are two variables. We want to know if these are the particles of the medium, we want to know any particle after time t, where is it? So, after time t, that means t is one variable, t समय पर से कौटी अच्छी. अच्छा पुणी सबू पार्टिकल तो एका डिस्प्लेसमेंट नहीं हेबनी तांकर. आई हैव ऑलरेडी टोल्ड यू बिकॉज द डिस्टर्बेंस विल रीच देम एट डिफरेंट टाइम्स. कहा को से डिस्टर्ब आग करुच्ची कहा को पछरे करुच्ची. तेणु यू कैन नॉट से दैट डिस्टर्बेंस जिते बड़े कला डिस्टर्ब कला से मोशन आरंभ हम. ऑसिलेटरी मोशन टा समान समस्त एम्प्लीट्यूड लेट अस से दैट ऑल ऑफ देम विल हैव द सेम एम्प्लीट्यूड किंतु समस्ते मैक्सिमम पोजीशन को एका टाइम रे पहुंचीबेनी. सो इफ आई वांट टू नो द पैटर्न, where are the pattern which tells us the position of the particles, I have to find out at time t where is the particle, not only one particle, for all of the particles. तामाने ए पार्टिकल टा कोठी अछि, ए पार्टिकल टा कोठी अछि, ए पार्टिकल कोठी अछि जदि मु जानिबी, आई विल जॉइन देम, लोकस बाहर कर देबी, मु कहबी दिस इज द पैटर्न. तामाने इक्वेशन ऑफ वेव बाहर करिया को हेले मोर जानिबार अछि जे व्हाट इज द डिस्प्लेसमेंट ऑफ ईच पार्टिकल आफ्टर टाइम t. व्हाट डू आई मीन बाय ईच पार्टिकल, तामाने केमती कोन काहा को मीन करी कहबी. तामाने इफ x changes, x determines the position of the particles. Let's say a particle is at distance x from the origin. This is my origin, O is my origin, and from the origin there is a particle at x. A particle at t time pore, after time t, where is it? Where is the particle after time t? Now, that means there are two variables now, t and x. So, my wave function will be a function wave solution y, if y is my displacement. This displacement may be position displacement, may be pressure difference, pressure variation, anything. So, that displacement is a function of x as well as t. कारण x चेंज है माने मु ता माने कहूची विभिन्न पार्टिकल रो x अलगा अलगा तापरे t टाइम पर केते समय पर मु बाहर करिया को चाहूची त मन t तो निश्चय वेरिएबल हबो. सो इंडिपेंडेंट वेरिएबल मोर एठला t and x and y will depend on x and t. That I want to find out first thing, that मोर का कोन दरकार, that x and t are the independent variable. मु जदि विभिन्न x पाई at time t what is the displacement बाहर कर दे परिबी, then I know the pattern of the wave, or that is my equation of the wave. First thing. Then the knowledge, what knowledge we have, that the particles will actually oscillate. Particles oscillate in SHM. तामाने सिंपल हार्मोनिक मोशन रो जहा डिस्प्लेसमेंट जहा जो सॉल्यूशन थिला सेटा ही हबो सेमानक डिस्प्लेसमेंट. किंतु को टाइम रे तांको पाखरे पहुंचला, कोठू आरंभ हैला तांकर डिस्टर्बेंस ता तांको केते बेले तांको डिस्टर्ब कला, आ कोठू टाइम ता मु मेजर करले a sin omega t हबो. दैट इज द थिंग, दैट y will be something like y will be equal to some a sin omega t. कहार फर्स्ट पार्टिकल जे x जहा पई x 0, if x is 0, फर्स्ट पार्टिकल जोठू आरंभ हैला, डिस्टर्बेंस जोठू आरंभ हैला, से पार्टिकल रो जदि t टाइम पर मु नेबी कोठी अछि बाहर करिया को चाहिबी, दैट पार्टिकल इज ऑसिलेटिंग इन सिंपल हार्मोनिक मोशन. आउ सिंपल हार्मोनिक मोशन रो डिस्प्लेसमेंट इक्वेशन होची y इज इक्वल टू a sin omega t. से जिते मीन पोजिशन रे थिला सेते मु आरंभ करी तेणु मोर फेज नहीं कि जीरो थिला इनिशियल फेजटा तेणु मु लिखी ए साइन ओमेगा टी प्लस फाइ लिखिनी ओमेगा टी खाली लिखी सो वाई इज इक्वल टू ए साइन ओमेगा टी टेल्स अस आफ्टर टाइम टी कौ टाइम टी कौठू आरंभ है टाइमटा जिते ये मेन पोजिशन रे थिला सेते जदि मु घंटा ऑन करी टी टाइम पर यही पार्टिकलटा एतिकी डिस्प्लेसमेंट रे हेइथिबो दिस इज व्हाट इट टेल्स यू बट व्हाट आई वांट इथरे तो एक्स जीरो पाई सिना मु कहि देली किंतु आई वांट टू फाइंड आउट फॉर डिफरेंट एक्स वैल्यूज now let's say that a particle is at x एई x particle को रो t टाइम रे मु पोजीशन जानिया को चाहूची एया तो कथा the wave let us we have the wave is traveling with speed v let us say from left to right then x distance जदि v स्पीड रे जाउची x distance जीवा पई ताकू लागिवो टाइम लागिवो केते टाइम इट टेक्स टाइम टू रीच x इज इक्वल टू x by v यूनिफॉर्म स्पीड रे से जाउची तेणु x by v टाइम ता माने आरंभ रु जदि मु टाइम धरिबी आरंभ रु से एई o को आग डिस्टर्ब कला केते समय पर x वाला को डिस्टर्ब करिवो दिस लेट्स से a पार्टिकल a o को डिस्टर्ब करिवार केते समय पर a को डिस्टर्ब करिवो ना x by v टाइम पर ताको डिस्टर्ब करिवो अच्छा यार जदि एठू t टाइम मु जेते बेले याको डिस्टर्ब कला t टाइम पर से एठी यार डिस्प्लेसमेंट y से अच्छा व्हेन टाइम वाज 0 सेते बेले a कोठी थिला a रो डिस्प्लेसमेंट थिला 0 व्हेन द वेव रीचेस हियर दिस पार्टिकल कोठी जाई पहुंची थिबो सेटा जदि मु बाहर कर देबी देन आई फाइंड द वेव इक्वेशन सी a पार्टिकल रो t टाइम धरा जाऊ t टाइम रे a पार्टिकल जोठी भी अछि सी x by v टाइम रे at time x by v a पार्टिकल टा जस्ट 0 रे थिला सेठी डिस्टर्बेंस पहुंचिला ओ जो पार्टिकल टा थिला सी केते बेले 0 रे थिला ताठू x by v पूर्वरु बिफोर x by v टाइम से 0 रे थिला मु बर्तन चाहूची जे या पाक यार याको डिस्टर्ब करिवार टी टाइम एट टी टाइम ये जोठी रहिबो ये x by v टाइम रे जोठी थिला 0 रे थिला ये तार x by v पूर्वरु 0 रे थिला तेणु मु चाहूची x रो जो पार्टिकल अछि सी टी टाइम रे जेतिकी बाट जाइथिबो ये सेते बेल को केते टाइम रे सेतिकी बाट जाइथिबो एई पोजीशन रे से केते बेले पहुंचिथिबो ना t माइनस x by v टाइम टी टाइम रो x by v पूर्वरु सेठी पहुंचिथिबो ये x by v रे देखो 0 रे थिला ये ता पूर्वरु x by v टाइम पूर्वरु 0 रे थिला ये t टाइम रे जोठी पहुंचिबो x वाला t रे जेते बेले पहुंचिबो ये t माइनस x by v टाइम रे सेठी थिबो से तापर t टाइम रे से ऊपर को कुआडे पळैथिबो किंतु t माइनस x by v सामरे एई पोजीशन रे से थिबो सो व्हाटएवर इज द पोजीशन ऑफ so the displacement of a at time t or this is the a particle at time t is same as the displacement of particle o before x by v time that is at time t minus x by v ये t टाइम रे जते कि डिस्प्लेसमेंट यार हबो ये ता पूर्वरु x by v टाइम पूर्वरु सेठी पहुंची थिबो तेणु सेटा तार डिस्प्लेसमेंट ना आमे जानिचु जे t टाइम रे से O वालार पार्टिकल माने this is the displacement of O, this is displacement of O particle. तेणु से डिस्प्लेसमेंट ऑफ टी टाइम रे एतिकी तबे टी माइनस एक्स बाय भी टाइम रे केते ना दैट विल बी इक्वल टू ए साइन ओमेगा टी जगह मु लिखिबी टी माइनस एक्स बाय भी. देन दिस इज द डिस्प्लेसमेंट ऑफ पार्टिकल एट ओ at time t minus x by v, but this is equal to the displacement of the particle A which is at x distance from the origin at time t. तो आमर एटा ही दरकार हेले x रो वैल्यू विभिन्न पुट कर देले आमे सब पार्टिकल मानकर y बाहर पाई गले. सो y is equal to this is the equation of the wave. So this is my equation of wave. I can write it in different forms. I can write omega रो value को अलग अलग लिखी करी. I can put it in different form. I have taken it here no initial phase. We can always start the initial phase to be 0 and write the equation where A is the amplitude, the maximum displacement of the constituent of the particle. एटी wave रो displacement किछि नुहे. wave तो आगु को जाउची तार displacement कोन डिस्प्लेसमेंट कहार पार्टिकल मानकर डिस्प्लेसमेंट कन्स्टिट्यूएंट्स ऑफ द पार्टिकल मानकर डिस्प्लेसमेंट हाउ दे आर ऑसिलेटिंग से जेतेबेले मैक्सिमम पॉइंट रे पहुंचला सेटा एम्प्लीट्यूड एंड दैट इज द आल्सो द एम्प्लीट्यूड ऑफ द वेव. सो एम्प्लीट्यूड ऑफ द वेव बहुत पिला लिखती मैक्सिमम डिस्प्लेसमेंट ऑफ द वेव. वेव रो मैक्सिमम डिस्प्लेसमेंट नुहे. वेव तो आगु को जाउची तार तो डिस्प्लेसमेंट कहिबा को गले बड़ी बड़ी चलिबो. डिस्प्लेसमेंट एठी कहार मैक्सिमम डिस्प्लेसमेंट ऑफ द ऑसिलेटिंग पार्टिकल्स. ऑसिलेटिंग पार्टिकल्स किए द कॉन्स्टिट्यूएंट्स ऑफ द पार्टिकल ऑफ द मीडियम आर ऑसिलेटिंग. सो तांकर मैक्सिमम पोजीशन मैक्सिमम डिस्प्लेसमेंट इज द एम्प्लीट्यूड एंड दैट ए इज आल्सो द एम्प्लीट्यूड ऑफ द वेव. omega is 2 pi by t. So we will define all these things. What is amplitude of the wave, what is frequency of the wave, what is time period of the wave. टाइम पीरियड तामाने एठी सेही टाइम पीरियड जो पार्टिकल मानकर टाइम पीरियड हैला टाइम पीरियड ऑफ द वेव. फ्रीक्वेंसी ऑफ द वेव सेही फ्रीक्वेंसी ऑफ द वेव व्हेन ए वेव ट्रैवल्स it makes the constituents of the medium oscillate and the frequency of oscillation of these particles or constituents of the medium is the frequency of the wave. So differentiate between the wave and the particles. Particles or the constituents of the medium are oscillating. Wave is not oscillating. The oscillating particle ro speed अलगा, wave ro speed अलगा. Oscillating particle ro speed change होची. mean position रे maximum, extreme position रे 0 सेतिमाई से सेटु फेरिला. तेणु ट्रांसवर्स वेव केस रे परपेंडिकुलर हेई पारे, लॉन्गिट्यूडिनल केस रे पैरेलल हेई पारे. सो ऑसिलेटिंग पार्टिकल्स मानकर वेलोसिटी कहिले अलगा जिंस सेटा मीन पोजीशन रे केते टॉप रे केते मझी रे अलगा तळे अलगा. सो ऑल दीज थिंग्स आर डिफरेंट फ्रॉम द वेव मोशन. वेव रो वेलोसिटी कांस्टेंट गोटे जदि मीडियम चेंज होउनी इट इज मूविंग विथ ए कांस्टेंट स्पीड अहेड. लेफ्ट टू राइट जदि जाउची से लेफ्ट टू राइट गोटे कांस्टेंट स्पीड रे आगो को जाउची. सो डिफरेंशिएट बिटवीन द पार्टिकल वेलोसिटी एंड द वेव वेलोसिटी. सो मार्क velocity जेतेबेले कहबो कहार velocity wave or particle velocity you are saying. So wave speed is constant if it is in the same medium. So amplitude of the wave represents the amplitude of the oscillating particles. When wave travels it oscillates the particle of the medium. The maximum displacement of the particles of the medium is the amplitude of the wave. Time period similarly define करिवो. Time period कहार ना oscillating particle रो motion ro time period is equal is the time period of the wave. Frequency से through define करिवो. कहार frequency से particle मानकर frequency of oscillation is the frequency of the wave. Then angular frequency, your angular frequency is omega which is nothing but 2 pi f. So 2 pi by t. T is time period, frequency f, amplitude a. These things we have defined already. Now you have to be careful whether it is whose, you cannot write it of wave, it is the of the particles. Then we will have another thing which is wavelength. Eta wave ro. The distance travelled by the wave during one time period. तामाने गोटे पार्टिकल कंप्लीट वन ऑसिलेशन कला बेलू को वेव केते बाट जाइथिबो सेटा होची हमर वेवलेंथ. सो वेवलेंथ इज द डिस्टेंस ट्रैवल्ड बाय द वेव ड्यूरिंग द टाइम a particle of the medium completes one oscillation, or I can say this is the distance between two consecutive 2 points at same two. It is the minimum distance कर दियो. It is the minimum distance between two particles in at same particles in same phase. I have told you that a transverse wave consists of crests and troughs, a longitudinal wave consists of compressions and rarefactions. So, dita adjacent crest ଭିତରେ distance ଟା wavelength or dita consecutive troughs ଭିତରେ distance होची is wavelength represented by lambda. This is called lambda. So, if this is a wave, position of the particles at different point, then this is one crest, the wave is travelling disturbing the particles, ye gote crest, ye gote crest. So, a dita crest majire distance adjacent, minimum distance between two particles in same phase. These two particles are in same phase. So, this is my wavelength or consecutive distance between consecutive crests or consecutive troughs भी हो पारे. ए ट्रफ आ ट्रफ भीतर डिस्टेंस टा भी लैम्डा. सो और ए डिस्टेंस टा लिनियर डिस्टेंस ए बंकाटा नुहे एम ए ठारू ए पर्यंत ए लिनियर डिस्टेंस टा. सो ता माने v जदि ता स्पीड लैम्डा इज इक्वल टू माय v इनटू टाइम पीरियड t. तामाने ए पार्टिकल टा गोटे कंप्लीट ऑसिलेशन कर सारा बेलू को सी सेतिकी बाट आगु पळैथिबो. सो consecutive crests or consecutive troughs, consecutive compressions or consecutive माने लगातार एटा ता परटा नेक्स्ट जोटा आसीबो आउ दीटा छाडी के करले तो डबल हे जीवो नाही. compressions and rarefactions दीटा का कंप्रेशन हवा दरकार. कंजिक्यूटिव दीटा कंप्रेशन भीतर डिस्टेंस होची लैम्डा बा कंजिक्यूटिव रेयरिफैक्शंस दीटा कंजिक्यूटिव रेयरिफैक्शंस मध्य डिस्टेंस टा होची वेवलेंथ. सो वेवलेंथ इज द मिनिमम डिस्टेंस बिटवीन टू पार्टिकल्स इन सेम फेज इन ए वेव, और यू कैन से इट इज द डिस्टेंस बिटवीन टू कंजिक्यूटिव क्रेस्ट्स और टू कंजिक्यूटिव ट्रफ्स इन ए ट्रांसवर्स वेव, or you can say it is the minimum distance between two consecutive compressions or two consecutive rarefactions in a longitudinal wave. You can also say it is the distance travelled by the wave during a time a particle completes one oscillation. So, this is about wavelength and we will continue thereafter. Okay.